Recorded, rolling. It's Tuesday, January 13th. So I'm going to go over lesson 7.4 with you guys today, geometric sequences. There's a couple of Alex assignments that I put the due date both on this coming Friday. So 7.123 and then 7.475. I'll go over 7.5 with you guys tomorrow. Thursday will be an Alex day. And then Friday, I'll get you guys your module 7 quiz. Another detail here. Next Friday, it's not this coming Friday, but the following Friday, there's a senior panoramic. You guys will be pulled out of class first period, I think. And I think there's also club photos going on that day, so throughout the day. So if you're in a club, then get an update on when your club photo would be. Yeah.
What's a panorama?
Pan is like you're panning around, panoramic. So if you guys see those photos where like there's like a bunch of people all like this, and it's like super wide and skinny. Yeah, but maybe everybody's on the bleachers usually. Yeah. So they're gonna get all the seniors. I think what they'll do is get all the seniors on the bleachers in the gym. They'll get like a really wide, skinny photo. Yeah, that's kind of right. Yeah.
So we have nothing to do with it.
Well, if you're a senior.
Oh, okay.
Yeah. Okay.
Okay.
Yeah, if you're senior, first period, about a week and a half from now.
Yeah.
All right, but geometric sequences. So here, I want to hit these ideas with you guys, and then do some puzzles from the book, and then walk around and figure it out. All right, so a sequence is like a number. A set of numbers has some pattern to it. Right now, back in module 2, I think it was, you guys saw arithmetic sequences. That was if there's some common difference from number to number. And here spells out. So if it was an arithmetic sequence, it took the form like the nth term, so a sub n, the nth term could be equal to the first term plus, and then there was some difference times n minus 1. Okay. And this is a lot like y equals mx plus b, or something like that. But it's like shifted a little bit. This was discrete rather than continuous, right? So it's a lot like linear equations, but a little bit different. Right? But now we're going to go to geometric sequence. Okay. Where you're not adding some difference, so it doesn't create a linear type line. What you do is you're multiplying some difference. So there's some common ratio. Okay. Now there are two forms that you can express the geometric sequence in. There's an explicit formula, which looks a lot more similar to formulas you usually see in this class. There's also something called recursive. So I'll show you guys both those, but one at a time. Okay. So let's start with explicit. Explicit formula. Yeah. So this is to say, like the nth term is equal to the first term in the sequence multiplied by some common ratio to the power of n minus 1. Okay. So this is, here I'll spell this out. This is the nth term.
Well, yeah.
This could be the first term. Okay. This R is what's called the common ratio. Okay. And then, well, n is the term number. Okay, so if you had like the first term, guys, what if you plug in 1 for n? What is 1 minus 1? 0. What's anything to the power of 0? Is 1. Okay. So then the first term would be equal to the first term. Right? You guys see how that kind of snaps together? Now here, okay, now if that clicks to make sense, awesome. If not, then I'll do an example or some examples with you guys pretty soon. Okay. But I do want to get this other form on the page 2. That's called recursive. Okay, so these are both subsets of geometric sequence. Okay. What if I have a recursive formula? Okay. Now, recursive formula looks a little different. It goes like this. You name the first term. It is so I'll say A1 is given. And then you say that the nth term, so A sub n could be the nth term, just like before. Okay. It's equal to some common ratio multiplied by the previous term. And the previous term, I'm going to do A sub n minus 1. Okay. Now, here, guys, be really careful here. guys, look here. So you know how to do math. Look here. If you see n-1 in a superscript, like up here, that's a power. So if you want like the fourth term, you do 4 minus 1 is 3. You do this ratio to the power of 3. Okay? But if you see n-1 as a subscript, it's like naming that term. So this n-1 right, this a sub n-1 refers to the previous term. Okay, is what that would be, right? And then oftentimes you also see comma n is greater than or equal to 2 tagged on, right? Because you have to get to at least the second term for this formula to kick in. Because the first term is some value that's given to you. Okay, right. So the key is key difference between what we're doing now versus what we did in module 2. Module 2 is like we were adding some common difference, right? And this looked pretty linear, like y equals mx plus b type. It's kind of like y equals mx plus b. Right? But now we're going to multiply. Right? So we're like, say if r is 3, we're multiplying by 3 times 3 times 3 times 3. We're constantly tripling. Okay? And so let's jump into some examples. Right? Maybe this will make more sense if you guys see some numerical examples of these. So, okay, starts on page 29. Okay. Of course, I already pre-recorded a much longer video where I do a ton of examples. I'll just do some of these with you guys here. All right, how about, this number 4 looks pretty good. So number 4 from your book is on page 33. Page 33. 33. This number 4. So I see this sequence of numbers. We got 400, 200, 100, 50, 25, comma, dot, dot, dot. Okay? Now, guys, do you see a pattern? Yeah.
Are you going to discuss summation?
Guys, this is not, not today. No. What we're looking for is like some pattern from one term to the next term. Yeah, and guys, what's the pattern here? Yeah, so times half, right? Times half, and then half. Okay, we keep going half, half, half. You see that? Like half, 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 half. Right? And so how can you express this either as with an explicit formula or with a recursive formula? How can you do it either way? So let's start with the explicit formula. And I told you guys the form goes, the nth term is equal to the first term times some common ratio and then to the power of n-1, okay, where n is the term number. Right. Let's try this out. Okay. So the nth term, that's kind of like saying y equals, but I'm saying the nth term. What do you guys think I'm going to plug in for A1? No, here, guys, everybody look up here. Look up here.
400.
Yeah, exactly. Yeah, you guys hear cut? 400. 400. Because 400 is the first term. That's what A sub 1 is. 400. So whatever the first term in the sequence is. Okay. What do you guys think I plug in for the common ratio?
1/2.
Yeah, 1/2. So we're gonna start at 400. We're gonna multiply it by a half to get to the next term.
Just do
Okay. Huh?
Just do
But yeah, which is 200. Yeah. Right, so if you do this one time, you get to 200. Or okay. And then this n could be any term number. So I'm gonna leave it sort of. You could sort of think of like x, or x could be like n-1. Okay. Let me show you guys that this does work. So I'm claiming that this expression should be able to explain this entire sequence. Okay? In fact, you could predict. See this dot 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 here. Maybe this could keep going on forever. Okay. And I can predict like the 10th term out. Okay. So let's see if this works. Let's plug in some values. So what if you plug in 1 for n? Guys, what is 1 minus 1?
0.
0. What's 1/2 to the power of 0? 1. And what's 400 times 1? 400. Aha! And is it the first term 400? Right. Let's go to the second term. I mean, you know the answer should be 200. Let's see if that's true. What's 2 minus 1?
1.
1? What's 1/2 to the 1?
1/2.
1/2? What's half of 400?
2.
Ah, it's 200. Ah! Right. Let's do one more. How about the 1, 2, 3, 4, 5? Let's do the fifth term. You guys ready to do the fifth term?
Yeah.
A little trickier. What's 5 minus 1?
4.
4? What's 1/2 to the power of 4?
1/32. 1/32.
1/2, half. 2, 4, 8, 16. I think it's 1/16, isn't it?
Oh.
1/16? Right. What's 400 over 16? It should be 25 if this works. Let's see if it works. Yeah, it did. Okay, guess it. Okay. Now that's an explicit formula. But there's a different way to describe the sequence, and that's with a recursive formula. So let's look at recursive. Okay. So recursive, you're given the first value, which is what's A1 equal to again?
400.
400. Right. And then textbook goes comma. Right. And then it says the nth term is equal to so I wrote this before. I said it's the ratio times the previous term. Guess that? The common ratio times the previous term. So how do you write it for this particular sequence? What do I write right here? Half, because that's the common ratio of, and then for the previous term, that's a subscript n minus 1. Okay. Okay. And then one more little detail. I'll do comma, and that's applicable to n is greater than or equal to 2. So you need to get to the second term for this whole process to kick in. Okay. Right. And that can be the recursive formula. Right, guys, yeah. All right. See what else to see here. Let's do all right, one a little bit different. Okay. Let me do example 6 here, and then I think that'll pretty well cover a bunch of these examples. Okay. It says find 4 geometric means between, so this is example 6 on page 32. Okay. The 4 geometric means between 243 and 32. Now 4 geometric means, what that means is that I multiply 243 times something, I get some second value. And then I keep multiplying that common ratio. I got a third value, a fourth value, a fifth value. Okay. And then the sixth value would be 32. Okay. So with again, what the textbook says find 4 geometric means 1, 2, 3, 4 between 243 and 32. So really I have at least 6 numbers in the sequence. Okay. So I can do that. Okay. Well, what I can do is I can set up an explicit formula like we just did. So the nth term is equal to the first term times the common ratio to the power of whatever term number minus 1. Do that. Okay. And we can pop in values until, hey, maybe it'd be really nice to know what is this common ratio. Because if I knew the common ratio, I could figure out what go in these 4 blanks right here. Is that? Okay. So again, we're multiplying by something, right, until I eventually reach 32. Okay. So how do you think we could do that? Guys, based on what you're seeing here, how can I translate this into this so I can eventually solve for R? What can I put in right here?
40 blanks.
Okay, yeah, so here goes 243. Is your first term. Isn't A1 equal to 243?
Oh yeah, and then the
Oh, 32.
and is 30.
Yeah, this would be 32. Okay. Now, we don't know what the common ratio is yet. I mean, it is solvable. We're working towards it. Okay. But guys, what term number is the number 32?
The fifth.
6.
I think it's the 6th term, right? Because the first term is 243.
Oh no, yeah.
And 2, 3, 4, 5, 6. Okay. So where the end goes, I put 6. Right. Now, of course, you always subtract 1. So we've done like effectively 5 iterations. You can think of it that way. Right. A different way to think about this is okay. Maybe I should say a different way they could have defined this is if they defined 243 as the 0th term, and then if they did that, then you would never need this minus 1 up here, right? They're calling 243 the first term, and so you have to have always minus 1 as part of the formula. Right, so we got that. Right. Ooh, can you guys apply some algebra here? Can I do 32 divided by 243 equals r to the power of 5 now? Because 6 minus 1 would be 5. Okay. And I need to take the 5th root. Okay. And since this is a fraction here, guys, what is the 5th root of 32? What times itself 5 times is 32? 2. Yeah. What times itself 5 times is 243?
Wait, 34.
Like here, I know 2 to the 5. I can check it with the calculator. 2 to the 5 is 32. Got that. Guys, what to the power of 5 is equal to 243? Take a guess. About 3. Yeah, it's 3. And that's equal to R, which is the common ratio.
I'm gonna get that. 1.
Yeah. Okay. All right. Okay. So you guys can find the common ratio because. Okay.
Wait,
No.
and then
Huh?
never mind.
Yeah. All right. So I just took the 5th root of both sides. Got 2/3. All right. So now we can go back and we can fill in these blanks. Here, I'll switch my ink color here. So guys, if I take 243, what do I multiply by to get to the second blank? Guys, take 243 times what gives me the second value? Second term.
43 times 1/2.
2/3. 2/3 right here.
Oh, I didn't see
2/3. That gives me 162. Looks like these are all going to be whole numbers. Looks like. Right. And then what do? Multiply by what to get to the third term? 2/3. Right. But I'm kind of going through a recursive process now. I'm just going to take whatever the previous value was. I was calling this a sub n minus 1 on my paper. I'm just answering the calculator. I'm just multiplying over and over by this common ratio, which is 2/3. That brings me to 108. And then I can just keep hitting enter. Enter, get 72. Enter, get 48. Okay. Okay, guys, now that my calculator says 48, if I hit enter one more time, what number does it have to say? To bring this all around too close. 32? Is it 32? Oh yeah! Oh yeah! Math wins again. Okay. So there's some word puzzles in here. Like doing here. I'll at least point this out to you guys. Guys, family ancestry, and she's going back some number of generations, trying to figure out how many people are in her family tree. Guys, every time you go back a generation, you're multiplying by what? Yeah, by 2, because you have 2 parents. Each of your parents had 2 parents, and so on all the way back. Okay. So that's like this one here. I highlighted green, so I did that one. The main video. And then, Moore's law. Did I show you guys Moore's law the other day? I brought off that graph that showed number of transistors on a chip released by year. Yeah. Here. I'll go find it.
The situation is so bad, because their offensive line is horrible.
Right. So I think it showed this, but here, just worth seeing it again. Guys, have you ever heard that technology grows exponentially? And this is a really classic example of technology growing exponentially. Every one of these blue dots is a computer chip that was released commercially. Like here, this one here says ARM9TDMI, that was released in 1999. So by year, so it goes from 1970 to 2016. So it's just scaled linearly by year, right? On this axis at least. Right? You guys, do these points all line up in a straight line? They do, but there's a catch. And the catch is that the vertical axis is actually not scaled linearly. It's scaled logarithmically. This goes 1,000, 10,000, 100,000, a million, 10 million. Oh, so it's going by a factor of 10. Right. They could have done factors of 2 and it would still line up in a straight line. Just be, okay, something like that. But if the vertical axis was scaled linearly, then guess what curve all these points would follow? Be an exponential. All right, so that pretty well covers any question you get about those. I can walk around, help you guys out.